Hello everyone, welcome to our little workshop, Breaking the Ice with Deep Learning. The purpose of this workshop is to introduce basic concepts behind deep learning to help you, to guide you to train your first deep learning model, and so that in half an hour when you leave this room, you will know how to approach your future trainings. You can extend your knowledge, you know how to approach it. My name is Michał Pański. You can call me Michael, that's easier. I joined Restb last year as a deep learning engineer. I came to Barcelona in 2019 to do my master's degree in artificial intelligence. Before I studied computer science in Poland. I worked for a few years as a software developer. I was programming in C++ and Java, but I found artificial intelligence the most interesting, and that's why I'm here today.
Yeah, and I'm Albert Jimenez. I studied here in the house on HackUPC, but communication engineering. Then I switched a little bit to AI. I studied a master's in computer vision, and I also joined Restb last year. Before I have worked at some other startup doing computer vision and music-related stuff. And okay, let's start with the workshop. First, we will do a little bit of a theory introduction, but super short, don't worry. And then we'll get to the hands-on part that I hope will be fun. So before we start, just a couple of questions to see how we're doing. There's like no right or wrong answer. Could you raise your hand if you have ever trained a deep learning model? Okay, a little bit of mixed audience. Cool. And this is a bit more difficult, but have you ever heard of an activation function? Okay, cool. But don't worry, we'll start from absolutely zero. So AI, you've probably heard about it. It's a super hot topic. It started with lots of ifs and elses, but right now machines now make these intelligent decisions based on data and the patterns that they can find in the data. This field is called machine learning, and today we're going into a subset of this field, which is deep learning. The difference relies in that deep learning comprises all these methods, machine learning methods that look at the data, but they are based on neural networks. So next question is, what's a neural network? Super broadly, super fast, because we don't have much time. Neural networks are a bunch of neurons connected with each other. What's a neuron? An artificial neuron. You have one right there. It's actually just a unit that takes, in this case, 3 inputs, but it can be as many as you want, and it does some operations between them, and it gives an output. Super easy, no? The secret is a little bit in how do you order and connect these neurons. Normally what you have is like your data and a first layer of neurons that read your data, operate with it, and then the outputs of these first neurons are fed to a second layer of neurons. So you keep adding some complexity until you give an output for whatever task or prediction you want to make. Let's zoom in just for a second inside of a neuron. It's the same, but you can see that there are some other parameters. Actually, the operations that this neuron performs are super simple. It's just a linear combination of the inputs. So it's one input per a weight plus another input per another weight. So it's just multiplying and adding stuff. And then you add a bias. And with the result that you get, you go through a function, an activation function. So some neurons are activated. They have some value. But you can see that for many of the results, the neuron is just outputting 0, it's deactivated. So you can see a little bit of parallelization with what goes on in a human brain. Some information activates some parts of our brain, but not others. So this is a little bit the power of these neural networks. They only activate the relevant parts of it, and they can mimic any kind of combination of the data, really. You can see that these parameters that are in orange are the important ones. These are different for each neuron in our network, and depending on their value, we will get one result or another. So really the secret of deep learning, or when we say that we're training a neural network, what we're doing is finding good values for these parameters. Let's say that we already know what deep learning is. And let's go to another basic question. At Restb, we work with images basically, and today we were going to do an image classifier. So what is an image? That's an image of a cute cat, and that's how we humans see it. But as you probably know, a computer actually sees something more like this. An image is an array of data. Each pixel has a value. Normally, we have values from 0 to 255 because we represent images with 8 bits. And 0 is a black pixel, 255 is a white pixel. We're cheating a little bit here because this should be a black and white image. To represent color images, we actually have 3 arrays like this, one for the R, one for the green, and one for the blue component. No? But let's imagine something like this for simplicity. So, okay, that's an image, but have you ever thought of how a computer actually sees something? We're doing models that tell that this is a cat and not a dog, but how can a computer from a bunch of numbers actually have some sense of sight? This is a very complex topic. It's like the whole purpose of computer vision. But today we will introduce a couple of concepts to understand what we're going to do later, no? Which are filters and convolutions. So let's see. Imagine that we have an image, like an image of a handwritten number form. So instead of looking at the image as a whole, we can focus on small parts of it. So let's just take a pixel and its neighbors, and we can kind of compare them or do some operation. For example, we could compute the average of the pixels, or we could do the pixels on the right minus the pixels on the left, and this could give us some information. No? When we do this around the whole image, we kind of slide this filter or kernel that defines the operations around the whole image. This operation is called convolution. We get something interesting. For example, here, with a very simple kernel, we can see that what we are doing is detecting the horizontal lines or horizontal parts of the image. And we could do the same, for example, for the vertical lines. And these features could be useful to write a simple algorithm that tells that this is number 4 and not the number 3 or 7, for example. So this is a little bit of an introduction to how we are actually seeing stuff in an image. So let's suddenly scale this up and mix it with neural networks, and we get convolutional neural networks. So what if instead of manually defining these filters to find an edge or to find something, we use a lot of data and these architectures to learn these filters automatically. Like in convolutional neural networks, we feed the model an image, and it learns a lot of filters. It starts randomly, like looking at stuff in the image, and then we apply filters to the resulting images of applying the first filters. So we kind of stack this operation. What happens is the first layers of the model learn very basic stuff, like transitions from blue to red, or an horizontal edge. But as the model gets deeper and deeper, we learn more advanced stuff, like, for example, something that resembles a human face or a wheel, the texture of a wall or of grass. So the point of these convolutional neural networks is that they learn features that are very relevant to then make any kind of decision. Then this second part of the model is specific to the task that we want to do. For example, here we want to do kind of a classification. We have an image, and we have to say if it's a dog, a bird, or a cat, I think. So these layers that look a little bit more similar to what I said were neural networks, what they take is these features and they maybe combine the ones that are relevant to tell that this is a bird. It learns like relations with this data. I don't know if it's super clear, but let's continue. So classification is actually not the only task that we can do with these convolutional neural networks, as you probably imagine. We had in our stand an example of object detection, where you actually tell where the objects are. Or we can even do more advanced stuff, like asking a question about the image, or even generating images that didn't exist before. So yeah, it's really a field with many possibilities. But let's focus on a classifier that is maybe the most basic and the one that we're going to do today. And let's see how we would train it. So imagine that we have a dataset of dogs and cats. Here we have a very cute cat as well. And in order to train it, we need the data, like images of usually of cats and dogs. And then we also need a human to annotate, like this is a cat, this is a dog. We can do this like having an array. This position is cat, this is dog. So this is 1, 0, because it's definitely 100% cat. No? We feed the image to the neural network, as it is, and we get a prediction. Okay, the network is telling us this is 72% a cat. Okay, pretty good. But ideally, it would be 100% a cat, no? So what we do is compare the ground truth to the prediction. And this is a step that is called the loss computation. We calculate like a distance between this and that. And the final step, in order to train it, and here is kind of where the magic happens, is called backpropagation. So depending on this loss, what we do is start from the part of the network that is closer to the prediction, no? And keep changing a little bit those weights, those bias, these letters that were in orange before, no? And also the filters in the case of convolutional neural networks. We adjust everything a little bit so that if this model sees this image again, the prediction would be closer to what we actually want, no? And the training consists of doing this multiple times. When the model has seen the whole data set, this is called an epoch. And in order to train a model, we need multiple epochs of iterations. So we have a model that is trained. How good is it? Because probably after a few epochs, it will be able to correctly classify all your training data set. The thing is that we say that a model is good if it can perform as well with images that it hasn't seen before. Otherwise, it's kind of like cheating a little bit, no? So this is why when you get a data set, you always save some part of it that you don't use for training, and you will save it for afterwards to test it and say, okay, it's good, it's not good. Usually it's around between a 10 or a 30% of the data set. If you ever see something called validation split, apart from training and test, this is used to tune some parameters, for example, like for how long should I train the model, or for more advanced techniques. Usually we have like 3 splits instead of 2, but let's not get into detail with this. Finally, there are 2 big kind of paths to go when it comes to frameworks if we want to do deep learning. We have PyTorch and we have TensorFlow. A good thing about TensorFlow is that it has a higher level library called Keras that runs on top of it. And Keras is very good for starting because it's easier to use. There's a lot of examples and documentation, and you can do mostly anything. So that's why today in the workshop, what the code that you can see is Keras with a little bit of low-level stuff in TensorFlow, but mostly Keras. And oh, seems like we have an email. What could it be? Okay, I hope this email finds you well. Well, it's a bit late, but could you please train an image classifier with this new dataset? It contains the following classes: alley, park, and entrance hall. What can we get in like 15 minutes? Okay, and they want the accuracy to be over 95%. Okay, there are 300 training images, but I will try to get more. I tried to do it myself, but I'm not good in deep learning. Please help. Good luck. So, okay, let's try it now. I don't know if you have your laptops with you, but for this part, you can code with us with a notebook that we'll share with you. Otherwise, you can just follow what we're going to do here. Oh, yeah, if you have the laptop nearby, maybe we can wait 5 minutes or so.
So how many people have notebooks? Who has a notebook? I think that there are not many notebooks, right?
I guess it's okay. Very slow.
It was even better. Albert, can you maybe write down this URL?
Yes. like so you can change it. What is it? Like GitHub?
Yeah, just GitHub.com and then. Okay. I will show you how to do that. We I'm showing you how to do that step by step. We go to GitHub. Okay. Is everyone at this stage with me, or we have to wait a bit? Sure.
Do you see in the background? Should we zoom in a little bit? Of course. Maybe a little bit.
Yeah.
I put just.
Fine. Yeah, it's pretty late.
Guys, the URL to the notebook is in our channel, the Restb.ai channel in Slack, so you can get there and here. Okay?
I mean, you will have to like upload the notebook in maybe I will show this instruction one more time. You have to open Colab, research Google.com, and then import the notebook from GitHub. I don't know if everyone has already done this. Is there anyone that is not ready? Okay, so we can start then. So this is a training notebook that Xavi has prepared for us, and maybe it would be more efficient if we go down and click on this cell and run all the cells before, and then we can go through each cell. So I can explain everything. So this is running. First cell, it is downloading the notebook, then installing a necessary library to plot like our metrics collected during training. We unpack the data set, we import all the necessary libraries, and then here we prepare data. We load the images, prepare data for training, we organize them in tuples of image and label, and then we create a tensor-specific structure dataset that basically helps you to preprocess data, to load it, and to distribute it into batches that then are further used in training. We build two data sets, training and validation. Then we build a model. The model is based on an architecture that is available in Keras. It is available in Keras applications. Maybe I can show you quickly a table what Keras offers. There are a lot of architectures. These are state-of-the-art models that you can use in your notebooks without defining the whole architecture. That is very complex very often. We are using the simplest network for this workshop. We are using a softmax activation function, which ensures that the output is like we are using 3 units, and softmax ensures that these outputs sum to 1, so that each of the units reflects probability of a particular class, and we have 3 classes in our problem. This is a code that I'm not going to go into details here, but it is related to batch normalization layers. That it is a topic for another lecture. We are using one of the optimizers that optimizers calculate how the parameters should be changed every step during training. Then we compile the model, and then we execute training. This is a model fit, and then we can see how the training evolved. We can see that accuracy is 1. Accuracy is a metric that tells you how many samples were classified correctly. So the question to you is, if this accuracy is 1, then are we done with the workshop, basically? Is it a perfect model? Does anyone have any idea? So basically, I can tell you that although it seems that all the images that the model was trained on are perfectly learned, so the model is able to perfectly classify them. The problem is that the model can perfectly classify images that it has seen, but it can have a problem to classify an image that it has never seen. And we can see here, when we go to the bottom, there's a pretty nice tool which is called confusion matrix. It tells us how many mistakes and what kind of mistakes this model makes. And we can see that on the training data. Actually, I didn't mention that, but we have 300 images in our training data, and we have also our validation data set, which consists of 150 images in this problem. And we can see that it perfectly classifies unseen images. But let's see how well it can predict, how well it can classify images that it has never seen. Actually, yeah, it's pretty bad. It's even worse than I thought. So we can say that this model hasn't learned anything, basically.
It's saying now that everything is an entrance hole.
Yeah. So it's basically, I think that Xavi wouldn't be satisfied with this model. How we can solve this? Well, there are several things in this notebook that we need to apply. First, you will have to follow me in the code, or you can just watch the changes that I make, and we can see the results on the screen. We need to track validation accuracy, so that at each epoch we evaluate the model. We need to track it during training. We do this in this way. We add validation data, and if we have this validation accuracy will be computed at each epoch, so that we can see how well the model performs on the unseen data. Another thing that could be pretty useful here is to use a callback, that because the thing is that this every epoch this model changes, and it can be pretty good in the middle, and then it can be it can very well learn the training data, but it can fail on validation data later on. And we would like to have the best model that performs the best on this validation data. There is a tool which is a callback. It is a callback that helps that stores the best model so that we can store it for later evaluation, and we are sure that we are always having this best model. We can do that in this way. Just models, actually callbacks. Yes. Let's stick to validation accuracy. And then we will have to load this model later on for evaluation. We will have to, I don't know if I moved too quickly. Okay. We have to load this model in this way. It was Keras, I think, models. I think it was like that. And actually, as we see that basically this model it will not be good. We can also already apply some techniques that can help you to have something that works, because this model clearly doesn't work. The thing is that we don't have much data, and the network is completely initialized with completely random parameters. But there is a really nice thing in deep learning, which is widely used. It is called transfer learning. Transfer learning can help you to use knowledge that was learned by some model before. For example, we will use a model that was trained on 14 million images, and this knowledge is there available for you to take advantage of it. And this totally changes, as you will see in a moment, it totally changes the quality of your model. We are going to use it now. It is in Keras. It is super simple to apply. We will have to go to the cell when we define a model.
Remember when we saw before, the drawing of the convolutional neural network? What we're doing here is keeping the part that was learning the filters and the features, because it's relevant for us not to have features of faces, graphs, whatever that has learned on a super big data set of 14 million images. And we are just removing the final layers to learn these connections of the features again. This is what we usually do always when we want to train a neural network by ourselves. We are not Google or someone who has million images.
Yeah, so let's see how the training will how it will impact the training. Actually, also one important thing is that at each step, after each batch, there is this little update of the parameters, and when we use a pre-trained model, we have to change the learning rate to be a bit lower, because the model has already learned a lot, and we are just making very little updates. So I changed it to divided it by 2, and also let's change the number of epochs so that the training is a bit longer. And we have to execute then these cells. This one with the model, it downloaded the pre-trained model and loaded the weights. And then let's see how the training goes. now, as you see, well, maybe I'll actually zoom out. As you see, now at every epoch, after every epoch, we print validation loss and validation accuracy. Our goal is to minimize the loss, but accuracy is the metric that we are actually using. It is more human, maybe a human understands it more than a loss. And we can see that actually it changed a lot. I mean, the model now has already learned enough to, like, when we have 94% of accuracy, it's a pretty good accuracy. Xavi asked us to have 95 at least. But let's wait until the training ends, because I'll have a question to you. Has anyone executing this now, or yes? Right.
Nice. We're probably gonna get, well, we'll see what results we get. Maybe it's not the same.
We are curious about your result, because the thing within deep learning is that it is very stochastic, and there's a lot of randomness, and to be, for example, sure that some model, some architecture works well, you have to perform a lot of experiments with the same parameters to really understand what's happening. Well, I think that 95-33, it is already. Xavi is happy. Let's wait for. Sure. But in the meantime, we can also maybe plot those metrics. We can see that, like, we can see both losses, training and validation, and also the same for accuracy. And we can plot, we can load the best model that was learned, and then let's see the confusion matrix. So we can see that entrance hole was actually the best class, the easiest class to classify. There were zero errors zero confusions between park and alley, or entrance hole and park. It seems that park is also quite a good class. And we can well, there's also a classification report here, but this will be maybe too difficult to explain. But basically, there are several metrics that you can evaluate your model with. But this is also a topic for a different lecture. But what we can also do here, which would be nice, that we can see what images were misclassified. Let's wait for the results. Do you have it, maybe?
The final accuracy is 0.9460.
It is the highest one, or?
No, and one is 0.9550.
So it's the same. It's the same. Yeah. So we got the same result in the end. But like here, let's see like the misclassified images. For example, this one looks quite difficult. It is true is park, predicted entrance hole. Personally, I wouldn't be able to say, to distinguish those. And like what, because I don't know how much time we have, because it actually started a bit also later. So maybe because we prepared also some other part, which includes another technique that you can use when you don't have enough data. I mean, even if you have enough data, it's always nice to have even more. You can magically have more data by using data augmentation. Data augmentation changes the data randomly in various ways, so that the model, you have more variability in your data, and the model can learn much more. I don't think that we have time to do that, but if you are interested and you would like to do it by yourself, I have a notebook that I can share it with you, and you can do it by yourself, and you can see how more you can improve this accuracy. And we wanted to put some results here, but
actually have it if you refresh.
Yeah.
The two results that you have.
Okay.
Yeah. So if you remember, when we trained without the pre-trained weights, everything was classified as an entrance fault. So that's like random chance. It's 1 in 3. It's a 33% accuracy. Just by using the approach of transfer learning, we got 95.33. So that you have an idea of how important maybe it is to know this when you want to train something.
Yeah.
And yeah, we wanted to compare as well with a technique that probably would have boosted a little bit, but this is the biggest difference.
Yeah, this is very important to know, because like if you don't have enough data and you try to learn something from scratch, basically you can see that it's quite difficult. But even if you have just a little bit of data and you use a pre-trained model, your accuracy can be very good. There are a lot of advanced concepts. There is also a lot of math behind what we showed you, and like we hope that you find this interesting, what we showed you. And if you have any questions you would like to, we will be here. Yes.
Yeah. Which changes have you made to use transfer learning in the model?
Yes. So I can show it very quickly now. As I said, Keras Keras is a very useful library, and it makes things easy. Just changing from weights none to ImageNet is everything. That's all. I mean, of course, when you have some more specific problem on different kind of data, then maybe Keras doesn't have a model that would fit your needs, but for our problem, it was good. And in general, for visual data, it is very commonly used.
Just one slide, I think, and that's it.
Yeah, like we prepared some suggestions if you want to extend your knowledge, learn new things. Personally, like I really recommend Kaggle. I personally learned a lot on Kaggle. There are machine learning competitions. You have real problems. You can solve actually important issues there.
And if you want like a blog to search like how do I train a neural network, kind of similar to what we do today, or more specific topics, there's this machine learning mastery blog that is like a complete course on everything related to machine learning and deep learning. Maybe you can also start there if you're curious. There's a lot of theoretical and practical information about mostly anything.
Yeah. So, well, that's all from our side, but if you have any questions or you would like to come here to talk to us, we are available. And